Today we have to prove that A star algorithm is admissible in nature. Means it satisfies the property of heuristics. So from where should we start? This is the first question in case of proving this part. So now what we have discussed in the previous class, so we have to remember the first point about this A star algorithm. The first point is whenever we are using A star algorithm, we have to maintain two lists. One is open list and another one is closed list, right? And initially we have to remember this point, open and closed, both the lists will be empty. And how we start this algorithm? We start this algorithm by keeping the start node into the open list. So this was the first part you have to remember. Then eventually we will loop and until the goal is found. And we have other steps included in the algorithm. So we have discussed. Now there are some terms we have discussed about A star algorithm. That is, I have discussed that A star algorithm is locally finite. Then the second point we have discussed about A star algorithm is it is admissible, and the third term which is associated with it is monotonic in nature. Now let me explain this term one by one and then we will go for the proof. So the terms locally finite, admissible and monotonic all are applicable on A star algorithm. Now the term locally finite graph means it is the graph where none of the node of the graph have an infinite branching factor. So whenever we were discussing 8 puzzle problem, then we have found that we have many branches, right? And these branches will create the child nodes, right? So now first you have to understand the concept of locally finite. So first, in order to understand the term locally finite, we have to focus on the term branching factor. So this is the key term which is associated with this concept locally finite. So branching factor means what? So branching factor of a node refers to the amount of new nodes that can be expanded from this node. So this is known as branching factor. So in this case, the branching factor is 3. From this node, we have 3 branches, right? Now, locally finite graph is one where none of the node on the graph have an infinite branching factor. So if we have this kind of situation that we may have infinite number of branching factor from this node, then this kind of graph is not locally finite graph, right? So finite number of branching factor of a certain node in a graph, if exists, then that graph is locally finite, right? Now, we have to focus on the other two terms, admissible and monotonic. So we have already discussed about this term, the definition of admissible, but the definition of monotonic is not stated in the previous class. Now try to understand. Today our goal is to find out that whether A star algorithm is admissible or not. But this can be proved with the help of this property monotonicity. So these two terms are very much important, right? So what we have already discussed in the previous class, that is A star can be expected to be complete. Complete algorithm means that it finds a solution, and A star algorithm is also optimal. Optimal means it finds the solution with the lowest path cost, right? And I have already discussed the term admissibility means a heuristics is admissible if it always optimistic means it either underestimate the path cost to the goal or it provides a correct estimate for the path cost to the goal. So try to understand so how this admissibility is defined. It is totally defined on the factor cost, path cost, and how we have estimated the path cost. So we have one function, we know that fn equal to gn plus hn. I have discussed this term. So this term represents the path cost and it will help a star algorithm to evaluate the path cost in the most efficient manner. Now see by using all of these terms how we can prove that a star search algorithm is admissible and complete, right? So now let's consider the first term, that is admissibility of the A star algorithm. So how we can prove it? See, the first thing you have to remember that A star algorithm is admissible. How we can prove it? If it uses monotone heuristics. Now we have to focus on this term because the proof of admissibility is totally dependent on the term monotone heuristics. Now what is this monotone heuristics? See, a monotone heuristics is something that the cost, whatever cost we are estimating through the path of this graph, then that cost never decreases. Monotonic nature means whatever value we are getting, eventually that value will increase. It will never decrease. Means if we have the value 2, then 3, then 6, then 9, then 10, it means whatever we are estimating over here, it is increasing in nature. So it is monotonic in nature. So this is the concept of monotonicity. Now, this property does not hold for some heuristic functions. Means whatever cost we are estimating, we have to make this cost monotonically increasing. Now how it is possible? Means we never guarantee that whenever we are using some heuristics, it will be always a monotonic in nature. But we can make it as monotonic. How? So if I use this formula like Fm is equal to max of say some cost, say if we have list of costs, and always we will return the maximum of that cost. If we use this kind of formulation, then what happens? Always the maximum value will be returned among the available cost. So by using this formulation, we can make a monotonic heuristics, right? Now, in order to prove this fact, we have to understand one point. Now, let's start with the admissibility proof. See, I am just designing one graph, and this graph is partial, means it's not a complete graph. So, this part is not there in the graph. And see, we have one node over here in, and see, this is the goal node. And we have another node over here. This is known as G2, which is not a goal. Now you have to understand one simple term over here. In order to prove admissibility of A star algorithm, we need this type of graph. Now we have to understand what is the meaning of each and every term. See here capital G. Capital G means it is the optimal goal state. Means this goal state we have to reach. So we are considering, let's say G is the optimal goal state. Now we have to consider one term which is known as C star. See, C star means it is the optimal cost, path cost. Because in A star algorithm, each time we will evaluate the cost using the function fn equal to gn plus hn. So cost factor must be there. Now, what is this G2? See, G2 is known as suboptimal goal state. Now, what is the meaning of suboptimal goal state? Now, if you ask me this question, I will give you the answer like this. G of G2 is greater than C star. Means if C star is the optimal cost and if this is the goal, means we need to spend this C star amount of cost in order to reach G. But G2 is a goal whose reaching cost is more than the optimal cost, right? So if I reach G by C star, means I have spent optimal cost to reach the optimal goal. But whenever I am reaching to G2, why it is a suboptimal goal? Because cost of reaching G2 is higher than the optimal cost. So that's why G2 is known as suboptimal goal, right? So now using this assumptions, we will start this proof. But before starting this proof, you have to assume another thing. Suppose A star algorithm has selected G2 from the open list for its expansion, because in A star algorithm each time a node will be selected from the open list and it will be expanded. Now, for some certain reason, we have to think that apart from selecting the goal node, A star algorithm has selected suboptimal goal G2 for the expansion. Now see what will happen. Because our target is not G2, our target is G. If we can reach to G by using A star algorithm, then only we can state that it is admissible. But we are assuming that it is not selecting G, it is selecting G2. But why I am assuming it? Because I am going to use one mathematical term which is known as proof by contradiction. So we are going to prove this concept by using proof by contradiction. So initially I am just considering that A star has selected one suboptimal goal from the open list for its expansion. Right? Now we will proceed to the proof. I'm just drawing the graph again. So this is the graph. And since it is an incomplete graph, so this part is not there. In and say this is the goal G and say this is the suboptimal goal G2. Now here consider a node N on open list. So we will have the open list and consider the node N on this open list on an optimal path to G. So where this node N exists, this node exists on the path of the optimal goal. Here this is the position of N. So thus what we can write, so what we are considering, so consider a node N on open on an optimal path to G. So this is the position. So thus what we can write? We can write C star, that is the cost, optimal cost of reaching the goal. It is this one. Why? Because after n, then we have to spend some cost to reach to the goal G, and the cost of reaching to the goal G is C star. So always the value of the C star will be greater than the value of reaching the goal node n, right? So that's why we can write this. Because after node n, we have the goal node. So cost of this path is less than the cost of reaching the goal node. So that's why optimal cost C star is greater than the value of Fn. So this is the first consideration. Why it happens? Because this n exists in the path of the optimal goal path, that is G. Now, you have to consider another thing, that is, since n is not chosen for expansion over G2, so what we can write? So this part is not considered. What we have considered, that this G2 is now considered for its expansion. So this n is not chosen for expansion. So we can write that since n is not chosen for expansion over G2, then what we can write? We can write Fn is greater than equal to f of G2. Why we can write? See, why A star algorithm has chosen G2 over this n? Because now we can assume that the cost of reaching Fn is greater than the cost of reaching G2. That's why this path is selected, because whenever we execute the A star algorithm, we know that the node with the optimal cost or the node with the lowest cost will be selected. So here this one is selected, not this one. So from this, what we can conclude? We can conclude that cost of this one, that is Fn, is greater than the cost of G2, that is FG2. So that's why A star algorithm has chosen this G2. So this is the next thing you have to keep in mind, right? And now we can say that G2 is a goal state. So G2 is the goal state means what we can write? We can write that f of G2 is equal to G of G2. Because whenever any goal state is reached, so at that point of time, this value and this value will be equal. So that's why if G2 is a goal state, so we can write that f of G2 is equal to G of G2. Hence, what we can write? From this we can write C star is greater than or equal to G of G2. C star means the optimal cost and G of G2 means the subpath of reaching this G2, the cost of the path for reaching the G2. So this cost is greater than this one, but this is a contradiction. So what we can write? Thus we can write that A star could not have selected G2 for expansion before to the goal state G. So therefore A star is admissible in nature, right? So what we have done in nutshell? In nutshell, we have created one situation where we have two goal state. One is the optimal goal state and another one is a suboptimal goal state. And for proving the contradiction, we are assuming that A star is selecting this state over this path. So here what we are going to prove, that if this node is selected, then we will consider that the cost of reaching this goal is always less than the cost of reaching this node. However, the optimal cost is C star and it is proven that this optimal cost C star is not greater than equal to the cost of reaching G2. Therefore, we can prove that in any situation, A star algorithm never selects this suboptimal goal. Always it will select a goal that has an optimal cost path. So that's why A star is admissible. So in order to prove that A star is admissible or not, we have to use this kind of scenario, right? By using the definition of the admissibility, we cannot prove. So always we have to use proof of contradiction. So here you have to remember one point. In order to prove this one, first you have to write few points. I'm just giving you the points. You can make a note over here. So A star algorithm is admissible or not. Before proving it, you have to prove that what is the meaning of monotone heuristic, right? Monotone heuristic means whenever you have a cost, say any cost known as say f cost, this cost will never decrease. It will be always in increasing order. But what you have to keep in mind, remember this point. Whenever you are using simple heuristics, by default, simple heuristic may not be monotonically increasing, but you can create this one. How? So you have to write a function in such a way so that whichever costs are available, you will select only the maximum cost among all the available costs. So each and every iteration, always the max cost will be selected. So whatever value you are getting from this, it will be monotonically increasing in nature. So after stating this line, then you have to state two considerations. That is, what is G? G is the optimal goal, and here you are creating another goal, that is G2, which is a suboptimal goal state. And suboptimal goal state means you have to remember this point. If C star is the optimal cost, then this is the meaning of suboptimal goal. Means the value of this one is always greater than C star, than the optimal cost, right? So this is the second consideration always you have to mention. And then you have to mention the key term, that is, you are assuming that A star algorithm is selecting suboptimal goal for expansion from the open list. It is not selecting the optimal goal cost. So this thing you have to state, and then you start explaining the proof.